Okay, so it's a pleasure to have Tomasz here. Do I say it correctly?
Yes.
University of Warsaw, and then he's going to tell us about the Leavitt algebras of quantum quivers. Please.
Okay, thank you very much. So the plan of my talk is following. First, I would like to introduce some environment for speaking about quantum quivers, since classical quivers are populated in a category of sets. Then, of course, the category in which I'm going to speak about quantum quivers must be the category of quantum sets. And next, I will...
Tomasz, I'm sorry, but I have to jump in right now. One has to bear in mind that quantum quivers, as Tomasz understands them, has nothing to do with quantum graphs, as people understand.
Quantum graphs is a misnomer. Because
It's not my invention.
people are calling quantum graphs the following construction. They are taking the adjunctions in matrix,
Yes,
and they are replacing entries of this matrix by some operators.
exactly.
And they call it, I don't know why, but it's a quantum graph.
Don't blame me.
Yes. So now you will see that my definition of a quantum quiver is closer to the classical situation, and the classical situation embeds in this quantum, in opposite what you said before.
Yeah.
So this is the difference. Okay. So how do you?
You can try to click on the touch.
Click and then arrow.
What?
Click on the dashboard.
Okay. Okay. So to understand what is about speaking math in some category, it is a difficult problem because people are so used to sets, the category of sets, they do not understand that it's a very special situation.
And you are upset about it.
No, I'm not upset. I'm stating a fact of life. Okay. So, in fact, people working in sets, in the category of sets, in fact, they are working in some topos. So, what is this topos? Topos is a category. I'm going to speak only about so-called elementary toposes. Okay, topos is a category having all finite limits, in particular a terminal object and having pullbacks. Second, this category is Cartesian closed, which means that for any two objects x and y, we have an object of maps, of mappings from x to y, which is denoted as an exponential. And third property is that there is something which is called the subobject classifying. This means that an object omega of this category has some universal monomorphism denoted by capital T, like truth, from the final object in this category to this object omega. And the universal property of this means that every other subobject A of an object X is a pullback of this universal one via something which could be called the classifying map chi M for this object X. Okay, so in the category of sets, the situation is very simple. First two properties are fulfilled almost for free. You mean that there are some standard constructions, and for the three, we know that every subset is tantamount to the characteristic function of this subset. Okay, so this subobject classifier is something like a universal characteristic function determining all subobjects. Okay. So, of course, the category of sets is an example of elementary topos. And every topos has something which is called the internal logic. And the internal logic of the category of sets is the classical logic with Boole algebras modeling propositional calculus. Okay, but in general, if you have any elementary topos, that internal logic is something which is called the intuitionistic logic, where models for propositional calculus are different. Boole algebras are replaced by so-called hating algebras. Okay, so for us, there will be interesting some very specific topos of algebraic, or rather co-algebraic origin. And my construction is based on the following observation, that if you have any locally small category, then the category of presheaves, which are contravariant functors from this category to the category of sets, is a topos.
Small category.
Sorry?
Locally small.
Locally small means that you have
Homesets are sets.
Homesets are sets, okay? Because people usually are using categories which are large in this context.
So that's homesets are sets.
It's a very traditional notion of a category, when you have sets of morphisms between objects. And then, when this category C, this locally small category C, is a trivial category consisting of a single object and single identity on this object, this construction recovers our topos of sets. So now let's take the topos of presheaves on some full monoidal subcategory C of the symmetric monoidal category of coalgebras over a field K. Okay? So in the category of coalgebras, we have some operations like tensor product of coalgebras, which is a coalgebra, and we have one-dimensional coalgebra K, and this K plays a role of a monoidal unit in this category. Okay? Okay, so speaking about this tensor product is the introduction, in fact, of some generalization of Cartesian products from the category of sets. So we have the following remark, that a quantum set is a symmetric monoidal category with respect to an argument-wise product. Because objects are presheaves, we can evaluate these presheaves. We are obtaining some sets, and these values can be to these values of this presheave. We can apply the usual Cartesian product. Okay, this kind of symmetric monoidal product is equipped with a unit, which is a singleton constant presheaf. Coalgebras of dimension 0 and 1 represent presheaves which are the initial and the terminal object in this category of quantum sets. Moreover, the initial object is monoidally absorbing, which repeats the property of the empty set. Empty set, Cartesian product of empty set with anything is an empty set. Okay? And the terminal object is a monoidal unit, exactly as singleton is a monoidal unit with respect to this Cartesian product. Okay, and therefore, since these two objects are classical, we will denote them by the classical notation as an empty set and a singleton, even if we are in much bigger category of quantum sets. Okay, so since we are in some exotic topos, then the internal language and the internal logic of this topos will be called quantum language and quantum logic, respectively. Okay, and now among these prefixes, there are some prefixes which are defined by coalgebras. There are so-called representable functors, representable prefixes of the form which is written. There is no.
Right on the wall.
Yeah, I'm showing you this place. By this, I'm denoting the home sets in this category. So there's a general fact that every category can be embedded in the category of prefixes of this category by something which is called the Yoneda embedding, which is of this form. Okay. Okay, so this category has some properties which are very close to the structure of the category of sets. First of all, for every object on some category, we can speak about some category of elements. The category of elements of objects in this category of quantum sets is a category whose objects are pairs consisting of a finite dimensional coalgebra in this category C and an element of the value of this prefix X on a given object of the category of coalgebras. And morphisms are described as it is written here. Okay. And then with this definition of elements, we can speak about some kind of quantum extensionality principle which applies also to quantum sets. But now, since we are talking about more complicated objects, this quantum extensionality principle is multi-layered. So first of all, the fundamental theorem of coalgebras says that every coalgebra is a colimit of finite dimensional ones. Okay, which means that
field, right?
Yeah, which means that similarly as sets are limits of or unions of their finite subsets or even singletons, okay, we can build our objects with some elementary ones, okay. Next, there is a fact that finite dimensional ones form a small subcategory of compact objects in this category of coalgebras. And finally, we have something which is called the density theorem, saying that every prefix on a small category is a colimit of representable ones. Okay, so these three layers on the level of sets degenerate somehow. Okay, they are invisible, but they are equivalent to something which classically is usual extensionality principle. So taken together, they can be regarded as some generalization, some extension, which is called the quantum extensionality principle. Okay. What is funny about this point of view? As you saw in the example of the Messier Jourdain speaking prose all his life, you maybe don't know, but you are using the notion of quantum elements all the time. So let's start from very simple examples. If S is a singleton, then we can linearize this singleton to a one-dimensional coalgebra and evaluate on this coalgebra the image under the Yoneda embedding of a linearization of any set. What we obtain by this evaluation is this set again. Okay, which means that we can reconstruct classical sets embedded via the composition of the linearization and the Yoneda embedding into quantum sets. Okay. Of course, if we start from an empty set, then we construct the empty classical empty set. If we start with a singleton, linearize it, and then apply this Yoneda embedding and evaluate on this one-dimensional coalgebra, we obtain again the classical singleton. Okay. Oh, this is not important. Next, more complicated examples of quantum elements. If we have a coalgebra, then in every coalgebra we can speak about group-like elements. What are group-like elements? They are values of the Yoneda functor applied to a coalgebra D on some linearization of some set S. And then this value can be characterized as a family of a group-like elements parameterized by this set S. Okay? It's in a sense, it's a family of group-like elements of the coalgebra D parameterized by this set S. Okay? Next example, primitive elements. Let's take the coalgebra consisting of a point, let's say, and an arrow, which starts at this point. This is a coalgebra whose structure is written here. And this coalgebra can be used to define primitive elements. What are primitive elements? First, take this coalgebra and evaluate on it the image of the Yoneda embedding of any coalgebra D. Okay? Then we have the epimorphism, the surjection, in fact, onto the same evaluation, but on the one-dimensional coalgebra. So these are group likes. Okay? And this set of evaluation of this Yoneda of D on this arrow coalgebra, this is a morphism surjection, which is a surjection of G primitive elements projecting onto their group likes. So, in particular, if you start from the group algebra, KG, which is a coalgebra, and if you try to find its points, elements, by evaluation on this element, we obtain group likes of this, which reconstructs the group itself. But when we apply this, for instance, to the enveloping algebra of a Lie algebra and evaluate it on this coalgebra, this arrow coalgebra, we obtain the Lie algebra in a similar manner. Okay? So this means that the group inside of the group ring or Lie algebra inside of this enveloping algebra can be reconstructed as quantum elements. Okay? There is a wide class of categories in which we can find very interesting quantum elements. This is the class of so-called categories of finite decomposition property. So it is obvious. We say that this category has this property if every morphism in this category has finitely many decompositions. Okay? And then we can associate with this category, we can associate a coalgebra whose structure is given by these decompositions of this element. Okay? And the co-unit of this coalgebra is 1 if M is identity and 0 otherwise. Okay. And then it turns out then we can describe C elements of this object represented by D as a family of functors of finite support. Okay, satisfying this condition. Okay. So here by f of c, I mean some object, some distinguished algebra regarded, associated with this category of quantum sets. It is also a presheaf whose value on the coalgebra C is the dual algebra of this coalgebra. Okay, so C star this time means the dual algebra.
Not system.
Yeah, sorry for that. Okay, and then in this algebra, regarded as a monoid, we can look at images of functors from this category D to this category consisting of a single element, where morphisms are elements which we are multiplying in the multiplicative monoid of this algebra. Okay, and then every such C element of D is nothing but a functor of finite support satisfying this condition. And let's see what we have here. Three examples. So if we take the monoid, additive monoid of natural numbers, okay, then of course it satisfies this finite decomposition property, and we have the following coalgebra associated with this. And what are these C elements of this quantum set? These are elements in this algebra F of C which are nilpotent. Okay, so nilpotents are quantum elements. Okay, if we start with a multiplicative monoid of natural numbers, okay, then applying the same construction, instead of nilpotents, we obtain finite families of commuting nilpotents parametrized by finite subsets of primes. So very interesting things. And at last, for instance, if we take the category of pairs of a finite set, on a finite set, then if we apply the same construction, then elements of this quantum set, which is represented by the coalgebra D, it's a system of so-called matrix units in this universal algebra F. Okay. Yes, please.
Previous slides. So,
if I could, yes, I can.
are these DIJs and previously DIs just some sequence of what is it? Because D is K or is formal variables.
Yeah, they are formal variables, not variables. These are not algebras. These are generators of coalgebra. So this is linearization of a set.
So it's a free algebra.
Not free, it's a coalgebra. Which is a vector space with this basis,
Yeah.
in which co-multiplication is given by this
Okay.
rules and epsilon. Okay. So matrix units or collections of matrix units in some algebra, okay, are also quantum elements. Okay. Also, finite dimensional representations of algebraic groups also are quantum elements. Namely, instead of C coalgebra, we take some special coalgebra, which is called comatrix coalgebra. And then, if V is finite dimensional, then the dual of these is the algebra of endomorphism of this inner vector space E. Okay? So elements of this shape of this coalgebra, sense, they are nothing but representations of the group G on a vector space G. Okay. So everywhere we look, we look, in fact, in classical mathematics, we see quantum elements of some quantum sets. Okay? Okay, so now, since we are going to speak about quantum quivers. So quantum quivers, there are spans. And a pair of the source map and the target map, they form a single map to the Cartesian square of the set of vertices from edges to. Okay. So we want to use this operation, but in the topos of quantum sets. So for that, we have to compare some operations on the category of algebras, okay, which is monoidal, but it's not Cartesian, with the kind of Cartesian product on the category of presheaves on this category of algebras. Okay. So how they could interact? Both are symmetric monoidal, and both are related by this Yoneda embedding. So the question is how these monoidal structures interact with the Yoneda embedding. To understand this, we have to introduce something which is called partial monoidal functor, which means that we have to introduce some full subcategory of the category of quantum sets, and we will call it partial monoidal if it contains a monoidal unit, and for any two objects in this category, in this subcategory, there is a sub-presheaf which is denoted like this in this category, which defines a sub-functor of the Cartesian product of values of these two presheafs. Okay? And to say that it's partial monoidal, it's not enough to say that this is not equality. It would be too stupid. It would give us nothing. But it must satisfy some properties. And these properties, written here, look almost like the axioms of partial monoids in the sense of Segal, but they are, but this also is extended to the realm of categories rather than monoids. And then we have the first theorem, the essential image under this Yoneda embedding of representable quantum sets is a partial monoidal symmetric subcategory of quantum sets. Okay? Where this kind of quantum Cartesian product as a subfunctor here is defined as a subset of pairs satisfying such an equation in the tensor product of these two quadrants. So the proof of the theorem is simply verification of all these axioms of Segal. Okay, so they are fulfilled. Okay, therefore we have the following corollary, that the Yoneda embedding of the category of coalgebras into quantum sets, which are presheafs on this category, admits a structure of a symmetric partial monoidal functor. And this is almost obvious, because there's the only candidate for the monoidal unit here. And of course, there are, in the definition of a symmetric partial monoidal functor, there is an absolute transformation of bifunctors. So this natural transformation is given by a very simple formula, where commultiplication of this in this coalgebra C, on which we evaluate both sides, enters in a canonical way. Okay. Okay. but it would be an empty art if we couldn't relate this with the category of sets. And the first theorem about the relation between sets and quantum sets is the following: that the composition of the factor of linearization, if you have a set, we take first a coalgebra whose a vector space whose a basis is given set, and next applying to this the Yoneda embedding. This composition gives you this embedding of sets in quantum sets, which is a symmetric partial monoidal full embedding. Okay, so this means that we can emulate sets in quantum sets. So imagine that the real nature, okay, of this world is quantum. Absolutely, absolutely. So why classical sets appear? What they are? They are very special quantum sets by this embedding. Okay. Okay. So I told you that this F was the dual algebra construction was a distinguished algebra associated with this topos. Okay? It turns out that in the sense of partial monoidality associated with this construction of this quantum categorical product, this quantum function algebra is partial commutative. In the sense of Segal, okay, which is nothing strange because we modeled our monoidal structure, partial symmetric monoidal structure on the axioms of Segal. Okay. What is the image of this embedding? If you have a set, then this set, regarded as a quantum set, can be described in terms of quantum elements of this linearization. Okay. It turns out it's a quantum complete set of orthogonal idempotents in this universal algebra. Okay, so this is another natural way in which these complete sets of orthogonal idempotents arise. Therefore, we can pick having, for instance, some object which is defined in terms of classical sets. We can, using this embedding, regard it as something quantum. Okay? And we call it quantization. Okay? And there's some logic behind this quantization. And it turns out that this logic of this quantization is precisely the Birkhoff von Neumann's quantum proposition calculus. If you maybe remember some rudiments of quantum theory, when questions we ask are phrased as some idempotents or some projections, okay? And when they are commuting, then we can answer, for instance, two questions forming a single question, which is the conjunction of these two. Okay. So Birkhoff and von Neumann started to model the quantum logic, starting from the quantum propositional calculus, based on this principle. And in this approach, this quantum logic appears in a natural way. Okay. One could ask, okay, so what about associative algebras? Associative algebras are vector spaces. Therefore, there are sets. So should we put them into this category of quantum sets and call them quantum algebras? The answer is no. The relation between algebras, in opposite to the situation with sets, is quite interesting and different. Namely, for every associative K algebra, we can define a presheaf on the category of coalgebras using the so-called free coalgebra construction of Swidler. Okay, but this construction written here makes this presheaf, in fact, the algebra of linear maps from this algebra C to this algebra A with multiplication which combines the co-multiplication in C and multiplication in A.
Convolution.
Like convolution. Yeah. So convolution with respect to C and usual multiplication in A. Okay. So this is called convolution multiplication. Okay. It turns out that this construction has some categorical interpretation. It is a free algebra for a monad which has this form on the category of K algebras. Okay. And this is the object which should be called the quantization of the algebra A. So the quantum algebra coming from quantizing algebra A is this free algebra for a monad. And in this way, we obtain a presheaf, which is called QR, of categories on the category of coalgebras, where the value of this home on two quantized algebras, which is a quantum set, evaluated on this coalgebra C, is nothing but natural transformation between these three algebras over this model. Okay? This is the definition. It turns out that in this way, something very well known pops up. This is the notion of Swidler measuring. Okay? It is well known that if you have classical algebras, then homomorphisms between algebras are very rare. For instance, if you remember, there is no homomorphism from Mn to Mn plus 1, which is unit. Okay? Of course, everything is unit.
Everything is
Everything is unit.
No, not everything is unit.
But there are no homomorphisms of unitary rings like this. All our algebras are unit. However, between such algebras could be kind of generalized morphisms, which are more complicated than homomorphisms. So homomorphisms, there are classical points of the left-hand side here. There are homomorphisms between algebras A prime to A. Okay? However, inside of these measurings, there could be, for instance, derivations, higher derivations, very complicated things, some Hasse differentials, okay, which are images. So this quantum set is an image under the Ionedas of the coalgebra of measurings from A prime to A, according to Swidler. Okay? So very big part of mathematics could be rephrased in this language. So let's come to quivers. So what is a quiver? According to Peter Gabriel, a quiver is the structure got by forgetting the composition law of morphisms in a given category. Okay? Which means that quiver is something maybe not algebraic in nature, like category, but it's something which we call proto-algebraic structure.
Sorry, but what does it mean in Cuntz-Pimsner?
This is the seminal article in which you can find.
But I want to know what it means. Just what the title is.
How in German?
I know that's in German. I know that's in
What does it mean?
or Polish or French.
It's like deep or deepened considerations So in part one, in part two, he developed theory about which Mateusz was talking. Okay. So since this is a proto-algebraic structure,
It's after 40 minutes, you begin your talk.
yeah. Since it's only proto-algebraic, we want to give it more rigid structure, and we are speaking about some algebras which are associated with these quivers, and people are interested in representations of a quiver as a functor from its path category to a category of vector spaces. Okay, and theorem about which Mateusz already were speaking shows that the classification of this or properties of the categories of representations of these algebras are very interesting. So besides this classical theory of Dynkin diagrams, we can, something is missing here. I lost something in these notes. Okay, so let me go straight to various path type algebras. So Mateusz started with path algebras. Next, you were speaking about Leavitt path algebras. There is some intermediate level of compass algebras. So there are algebras satisfying some of some axioms on this list. Okay, and it turns out that modules over these path algebras are quite interesting. Maybe not so much for path algebras, whose modules are nothing but representation of quivers, and there is this theory of representations of these quivers Mateusz was talking about. But for instance, for Leavitt path algebras, we know that finite geometry modules in general do not have invariant rank. These are phenomena which are quite different comparing with properties of classical commutative algebras, for instance. Okay. And why people are looking for these algebras? So there's a highway between combinatorics of quivers and algebra, which goes in two ways. So it's a kind of parallelism between combinatorial properties of a quiver and algebraic properties, for instance, of this Leavitt path algebra. However, as Piotr was explaining on many beautiful examples, conceptual picture explaining in detail how this parallelism could be obtained in conceptually is still to be unraveled. So first of all, we have a problem of functoriality. These are not arbitrary constructions, but they satisfy some kind of functoriality. For instance, Kirvasitu, Hayes, and Tobolsky consider this problem of dualizing push-outs to pullbacks of algebras. Okay, and then the following phenomena appear. First of all, morphisms between quivers have to be modified. Condition CK2 depending on regular vertices is a source of great difficulty. It's a very troublemaker. And then algebras, despite having an explicit presentation in terms of quiver, they are linear objects, and it is hard to control their functoriality in terms of the pure combinatorics of a given quiver. Okay? Okay, so now I will say a few words about new strategy which I propose. So first, I'm using resolution of singularities of a quiver to avoid difficulty with singular vertices. So now you can start thinking that this is some cheating. Something is too cheap, okay? But this makes sense because we are not going to describe Leavitt path algebras up to isomorphism, but up to some equivalence. And this approach is linearized from the scratch. Everything is in terms of some linear categories. And then it works even for quantum quivers. And this resolution of singularities is based on the pair of celebrated theorems. First one by Druine and Tomford says that every quiver with countably many vertices can be desingularized by adding tails to sinks and infinite emitters. Okay? And the second theorem says that every, due to Abrams and Aranda Pino, says that every Leavitt path algebra is Morita equivalent to the Leavitt path algebra of regular quiver. Okay? So if we allow some moves to desingularize our Leavitt path algebra, we can speak about our Leavitt path algebra as it was an algebra for regular graph up to Morita equivalence. Okay? Okay, so what are quantum quivers? It's very simple. Take the category of quantum sets and draw a diagram which you know from the category of sets. So, for simplicity, let's speak about representable quantum quivers. So they are represented by diagrams or spans of coalgebras. So we have a pair of coalgebra maps, like delta 0, like this, okay? Satisfying these properties, okay? Which could be recognized from what I was talking about, this quantum Cartesian product. This is precisely this property of the Cartesian product which allows us to speak about a pair of morphism of quantum sets where this pair, which is the source and the target for the quantum quiver, evaluated on an edge, which is now an element of this coalgebra of representing the quantum set of edges, taking values in elements of this Cartesian product. So the difference between this approach and that approach is that there's an operation of passing to the opposite coalgebra representing this set of vertices. Therefore, we can speak about vertices and opposite vertices here. And now, to speak about structure and functoriality of all constructions associated with these quantum quivers, we have to speak about correspondences. So correspondences, there are some actions of some coalgebras on some linear categories. So now we are speaking about the category of opposite category of coalgebras, of comodules, or over coalgebra C. This behaves like the category of modules over an algebra up to some set theoretical differences. Okay? So this is our model to understand. Of course, if we have this category, it is a prototype, it's a combinatorial prototype of something which could be made more algebraic. For instance, every comodule over this algebra C is a module over its dual algebra, or some restricted dual to this algebra. Okay, so having constructions on this level, you can easily pass to this more algebraic situation. But I will keep speaking about this rather comodules than modules for the simplicity. Okay, and then if we have two quantum sets, X and Y, and we have a morphism in this category of quantum sets, then with such a morphism, we have two functors associated with this morphism between the categories of this opposite category of comodules over these coalgebras. Okay, this is F lower star and F upper star, and they form a joint pair of functors, and they are described in a very easy way. We have two functors. This is the co-restriction functor, which is given by the composition of the structure of a comodule with a coalgebra map from C to D. Okay, and then we have a co-induction factor, F upper star, which is a cotensor product over D between this D comodule and this coalgebra C under this homomorphism from C to D, and it becomes a C comodule, right? C comodule. Because of this co-multiplication in C. Okay? And it's very easy to check that this is a joint pair of functors. Okay? And then we can speak about some generalization of some easy properties of sets. For instance, sets are discrete. However, on the level of these quantum sets, discreteness is not for free. If you remember, for instance, this coalgebra consisting of a point and an arrow, which is the source, for instance, of primitive elements, which is related to nilpotents and all this stuff. Okay, you see that these coalgebras could be non-discrete. For instance, the algebra dual to this algebra of this arrow is the algebra of the dual numbers, which is a one-dimensional algebra having non-zero dimension as an algebra. Okay? In this sense, it is not discrete. So not all algebras could be regarded as discrete. But the property of being discrete can be mimicked by the property of the existence of the left adjoint to this functor F upper star. So to understand what is going on, take an example. Take the coalgebra as a linearization of a set S. Okay? Then every comodule over this coalgebra is a direct sum of vector spaces parameterized by this set. Okay, and if we have two such linearization of a sets, then we can look for this. Look at these adjunctions. So in this situation, coming from classical sets, we have for free such an additional adjunction from the left, which reads as following. There is this middle F upper star functor, which encodes, in fact, this set theoretical map between these classical sets. Okay? And these two functors, the right adjoint and the left adjoint, they are very similar one to each other. The only difference is that here we are using the product over the fiber of this set theoretical map, And here we are taking the direct sum. Okay, but discreteness is about the existence of this function, this product over this function. However, this could be used as a definition. What should be the finite set or finite morphism, a quasi-finite morphism of these quantum sets? Because this map F between sets is finite if and only if the left adjoint coincides with the right adjoint. Such a situation when for a given function its left adjoint is isomorphic to this right adjoint is called the Frobenius function. And this pair of functors is called Frobenius pair. Okay, so we have a candidate for this functor to be quantum quasi-finite map between quantum sets. Okay, so it's the existence of this left adjoint and equality between this left adjoint and the right adjoint. It's quite quasi-finite. In the definition of a regular vertex of a graph, we have the condition that this source map is not only quasi-finite, which means that it has finite fibers, but it has what? Has the property of subjectivity. S is subjective. Okay. So the image of S is this subset consisting of regular vertices if they are not infinite emitters. Okay. So this means that you can take this property of this middle functor to define this subjectivity. This subjectivity means that F upper star is a faithful functor. Okay. So what is the regular graph? What should be the regular graph? Regular graph should be the graph for which this functor associated with this morphism S is first of all faithful and it is Frobenius. Okay. And then we can repeat almost everything. And so we have also some non-classical examples. So besides these classical examples coming from classical sets, we have very interesting properties of this quasi-finiteness and this being Frobenius, because they are related or they depend on the existence of some left adjoint functor, which is called cohom of Swidler. Okay, so there's quite a canonical way to provide examples of Frobenius pair of functors coming from morphisms between quantum sets. Okay, in terms of this cohom and isomorphism of this cohom with some cotensor product. Okay, so what is the quantum correspondence from X to Y? It's simply a morphism of representative quantum sets of the form F goes to this quantum Cartesian product. Okay, which composed with projections onto these factors of this Cartesian product provides us the notion of the source and target morphisms. Okay, and then with every now our goal is to construct something that generalizes the Leavitt path algebra, but this construction would go through the construction of something which is called the Cuntz-Pimsner monad. Okay, so Cuntz-Pimsner monad usually is defined in the context of Hilbert modules. it has some purely algebraic incarnation, which is called the Cuntz-Pimsner ring, which will appear in a second. Cuntz-Pimsner ring. Okay? But it can be produced, forgetting about all scalar products, Hilbert structures, and so on. It depends only on some adjunction. So what is this adjunction? So first of all, we have some endofunctor, Q. Let's say Q lower star, admitting a left adjoint. So in fact, it's some adjunction of endofunctors on some category C. And such adjunction has a unit and a co-unit natural transformations. And with such a notion, with such an object, we can associate its stable category. Stable category, denoted by STQ of this adjunction Q, is defined as a category whose objects are objects of this category C, being equipped with some additional data. So first of all, it is a retraction of Q lower star of n onto n, which induces a retraction after applying this Q upper star from this to that. This retraction has its idempotent, okay? And this idempotent composed with the co-unit preserve this co-unit, okay? So this is quite abstract condition, which can be written in terms of equations. So equations are like this. So we have a pair of two natural northeasts, okay, omega n and sigma n. One is a section of another, or another. The second one is a section of the first one, which is this condition. And since the opposite composition is idempotent, the image of this idempotent under this Q upper star also is an idempotent, and this idempotent preserves the co-unit. So this is a purely algebraic description of this thing. Okay, and such objects are related by some morphism in the stable category, and the morphism is something which is obvious. Okay, it's a morphism between objects in this category C, satisfying this pair of conditions, and compatibility with both omega and sigma. Okay. And then, definition. We define the Cuntz-Pimsner monad of the adjunction Q as the quotient of the free monad generated by the coproduct of these two members of this adjunction of endofunctors by the congruence generated by the following system of identities. Okay? You can meditate. Okay, these are equations, concrete equations. For instance, if we have a unital ring B, and we consider a B bimodule P, which is finally generated from the right, okay? Then we have such an adjunction. It's an adjunction of Q upper star, where Q upper star and Q lower star are following. Q upper star is a tensor ring from the right by this bimodule, okay? And Q lower star is the model from this P, okay? So this is similar to what Mateusz was talking about, speaking about projective and injective objects. However, since it is a finely generated projective as a right B module, this is the same as tensoring from the right by the dual, right dual to P, okay, which is also a bimodule. So these Q upper star and Q lower star are endofunctors and form an adjunction. Okay? And now, given such a bimodule, we can form an algebra. What is this algebra? We take the tensor algebra of this bimodule, which is the direct sum of P and P star, and divide this by the following idea. Okay, which is canonical, okay? eta is a unit of this adjunction, and epsilon is the co-unit of this adjunction. So this epsilon is simply the evaluation of this functional on this element of this module, and eta is simply the dual basis, okay, for a projective bimodule. Okay, and then we have the following theorem, that this Cuntz-Pimsner ring, which was defined by Arano, Pino, this Cuntz-Pimsner ring has its category of modules, and this category of modules can be characterized in such a way that the Eilenberg-Moore category of the Cuntz-Pimsner monad I defined in purely categorical way before is canonically equivalent to the state. So what is the Eilenberg-Moore category? Do you know? So Eilenberg-Moore category is the category of coactions, okay, of some monad, in a sense, which is there are two solutions of the universal problem of adjunction. We can ask, does a given adjunction, okay, come from the property of monadicity of some functor? Which means, can a given category of algebras, Eilenberg-Moore algebras over some monad, can be presented as the category defined in terms of the comparison morphism for some adjunction in monadicity context. Okay, so this pair of theorems say that first theorem says that this Cuntz-Pimsner monad of this adjunction defined as before by finding the projective from the right B model P is isomorphic to this Cuntz-Pimsner B ring of P. Okay, so category theory can be equivalently rewritten in terms of algebra. Okay, and second, again, the Eilenberg-Moore category of Cuntz-Pimsner monad, something is related with this, okay, is canonically equivalent to the stable category of the adjunction. Conversely, forgetting the retraction is monadic, and the resulting monad is the Cuntz-Pimsner monad. So this is a triple characterization of this Cuntz-Pimsner monad. Okay, it is given in terms of this Cuntz-Pimsner ring. It is given as a monad of some monadicity result, and the Eilenberg-Moore category, in fact, is equivalent to the category of modules over this Cuntz-Pimsner ring. Okay. Now, what is the Leavitt path monad? This time, we have to start with this quantum quiver, the quantum set of edges, vertices, and these two morphisms of quantum sets, S and T. And as I said, we call such a quiver regular if this S upper star corresponding to this source morphism is faithful and Frobenius. Okay, and then we can associate with such a quantum quiver a pair of adjoint functors, Q upper star and Q lower star. When Q lower star is decompositional like T lower star as upper star, which means if we have a span, this corresponds to this fact that first we are pulling back under this T upper star from V to E, and then we are pulling back with respect to this S upper star. Okay, and then we are pushing down along this T upper star. So in a sense, this is such an operation, okay, on the category of CV, sorry, and this is CV0, in fact, okay. This is, or maybe like this, okay. And then there is a subtlety, namely, if we have such an operation that a priori it relates these two categories when these vertices and these ones, these are opposite in nature. However, careful calculation shows you that you can define these two functors in such a way that, such a pair of morphisms from V0 to V, in fact, induces an endofunctor on the category CV. Okay? And then we obtain Q lower star. Q upper star is left adjoint. And now enters the discreteness of this source map. The existence of this S lower shriek is responsible for the existence of this endofunctor, which is left adjoint to this one. And then the Cuntz-Pimsner monad of that adjunction associated with this quantum quiver will be called the Leavitt path monad. And now example. So let V be a K-algebra generated by orthogonal idempotents, which are labeled by elements of the set of vertices of some regular quiver. Okay? Let's define a B bimodule generated by elements labeled by edges of this usual quiver. And then we introduce the bimodule structure. Right multiplication of these elements of this module PE by this idempotent 1V. Of this algebra generated by orthogonal idempotents. Of B generated by these things. So these are idempotents corresponding to vertices. Okay. Then we define a bimodule. Okay. Provided this bimodule is regular. Okay. Okay.
So B is generated by edges.
Yeah, and let's assume that we have finite number of edges. Okay, also. Then it's a simplification, showing that the very canonical definition of a bimodule structure, and of course making this for sure right projective, finite projective, leads to some bimodule. And this bimodule we call algebraic autocorrespondent, defined by the regular quiver. This is a classical quiver. Okay? And then we have the theorem. For every regular quiver that the Cuntz-Pimsner monad of the algebraic autocorrespondence on the category of B modules defined by the quiver is isomorphic to the tensor ring over B with the Leavitt path algebra of that quiver. Okay, so look at this. Oh, sorry, it is not this. This is the most economic way of writing the Leavitt path algebra. Do you agree? There's almost nothing here.
I think you deserve the Balcerowicz award for something like that.
Okay. Okay. So now we have theorems about this construction. So first of all, for every regular quiver, the Cuntz-Pimsner monad of the algebraic autocorrespondence defined by the quiver is isomorphic to the tensor ring over B with the Leavitt path algebra of that quiver. Okay, so this is the, deep source of Leavitt path algebras. Okay. With such a, if you remember, we defined for any Cuntz-Pimsner monad, we associated its stable category. And stable category for these Leavitt path algebras, which is a special case of this Cuntz-Pimsner monad, have a special structure. So by the definition of the Q lower star and this adjunction between T upper star and T lower star, the morphism omega n is equivalent to a morphism T upper star n to S upper star n. Anybody studying algebraic geometry knows that this is the transition. So if this T and S were source and the target of some groupoid, then this would be the transition function. Okay, but this transition function for groupoid must satisfy also this condition of the cocycle corresponding to the composition in this groupoid. However, what is our quiver? Quiver is some category without composition. So anything like that should be regarded as a representation of a quiver. Okay, so this is a representation of a quiver. What you were writing element-wise, okay? So written in terms of these functors is actually the representation of a quiver. But it is not the only datum which is related, which is associated with our construction, because we have besides this omega n, we have also this section sigma n. Okay. So this sigma n is something like wrong way map. It's something like conditional expectation in probability theory. It's something like integration along the fiber of some submersion. Okay, if you have some family of measures. Okay, so this is some operation. Okay, of this sort. So third representation of a quantum quiver is not only the representation in the sense of the classical representations of quivers, but also this stability condition by this, let's say, an analog of this conditional expectation. Okay, and then we have the following theorem using this terminology. So this is the I suppose this is the main theorem revealing the origin of Leavitt path algebra, relating this with stable representations of a quiver. So theorem: the Hilbert category of the Leavitt path monad of a quantum quiver is canonically equivalent to the category of stable representations of that quiver. Okay. So you remember this Eilenberg-Moore category of the Leavitt path monad was like a category of representations of Leavitt path algebra, which means simply Leavitt path algebra up to Morita equivalence. Okay, so Morita equivalence class on this categorical level is nothing but the category of stable representations of that quiver. Okay. If you replace all this categorical yoga by algebra, it produces automatically Leavitt path algebra. Okay, and conversely, forgetting about arrows in a stable representation of the quiver. So what is forgetting about arrows? Arrows are related with edges. Okay, these arrows. Okay, so you are coming back to this algebra generated in this algebraic example. You are coming back to this algebra generated by this idempotence related to vertices. So we forgetting about edges, and we're going down to to these vertices, to this algebra of idempotents parameterized by these vertices. So forgetting about arrows, in a stable representation of the quiver is monadic, and the resulting monad is the Leavitt path monad. Okay? Okay, so the last thing is about what Piotr was talking about. We are interested not only how to generate this from category theory or some, okay? We are also interested how this construction depends on canonical or natural mappings between these quivers, okay? So first of all, what is functoriality of the Cuntz-Pimsner monad? The theorem says that the Cuntz-Pimsner monad is functorial under the correspondences intertwining Q adjunctions, which means correspondences equipped with a natural isomorphism like this. Okay? So Cuntz-Pimsner is very simple. If we feed this Cuntz-Pimsner context with data coming from the quiver, then it starts becoming more interesting. Because then the functoriality of the Leavitt path monad looks like this. The Leavitt path, oh sorry, there's one T missing. The Leavitt path monad is functorial with respect to correspondences F, which intertwine the source functors. Okay? So correspondences are linearized, generalized relations. Piotr was talking about relations, okay? So these are relations compatible with sources, compatible with targets, and satisfy some additional condition, which is called the Beck-Chevalier condition. It's a strange condition, strange looking condition, because it mixes functors having upper star with functors having lower star. Okay? But this Beck-Chevalier, in fact, condition is in fact, in the algebraic context, tantamount to some square being Cartesian. It's a pullback condition. Okay?
So it's like target bijectivity.
Yes, so this is related to your target bijectivity. So many of your conditions disappear here. Why? First of all, no regularity. Irregularity is for free. Everything is regular. I know, I will disappoint you. But you have many more. You have many more conditions. Why? Because you are sticking to these relations. You wanted everything to be combinatorial. Okay? But since I'm not talking now about relations, I'm talking about correspondences, which are more flexible. They are linearized.
Mm-hmm.
Many of conditions from your list can be also erased. Okay? So this is the essence. Okay? What is from the very high point of view, very categorical point of view? What is the nature of functoriality of this construction of Leavitt path monad in general, and Leavitt path algebra in particular? Okay. So this is the message to take away. Thank you very much.
That case, we're gonna move the last, maybe 5-minute break and then.
Yes.
Okay, so let me stop recording.
I presume that